Hello everyone, welcome to Civil Galaxy. Myself Dr. Pruthviraj B S. In today's session, we shall see how to analyze a continuous beam with the help of Kanis method. So here in this beam, we can see span AB is having an eccentric loading of 50 kilonewton and span BC is carrying an UDL of 80 kilonewton per meter and span CD is having an central concentrated load of 100 kilonewton and the moment of inertia for span AB is I, for span BC is 2I and for span CD is 1.5I. So from the previous classes we know the first step in the analysis of Kanis method we use to calculate fixed end moments, to calculate the fixed end moments. So if I consider this first span AB, since it is having a eccentric loading, the formula will be minus WA B square upon L square, where W here is 50, so minus 50. A is this span, that is 2.5 meters from point A here, so it will be 2.5 multiplied by, this is the distance B, that is 1.5 square upon 12. So the answer will be equal to 17.58 kilonewton meter negative. Similarly, the fixed end moment from point B to A will be equal to, the formula will be plus W A square B upon L square. W here is 50, A the distance is 2.5 square multiplied by B. The B distance here is 1.5 upon 12. So the value will be equal to plus 29.29 kilonewton meters. Similarly, for span BC, fixed end moment from point B to C, since it is having a UDL, the formula is minus W L square upon 12, where W is 80. The total span here is 4 meters upon 12. So we are having a value of minus 106.67 kilonewton meters. Next, fixed moment from point C to B will be equal to, the formula remains same, only the sign changes, that is plus WL square upon 12. W here is plus 80, the total span is 4 upon 12, which will be equal to plus 106.67 kilonewton meters. Similarly, for span CD here, which is having a central concentrated load, fixed end moment from point C to D, for a central concentrated load, the formula is minus WL upon 8. W here is, the load is 100, so minus 100 upon the total span 3 divided by 8, which will be equal to minus 37.5 kilonewton meters. So next, fixed end moment from point D to C will be, the formula remains same, only the value changes, plus WL upon 8, which will be equal to plus 100 into 3 upon 8, that is plus 37.5 kilonewton meters. So if we observe here, the end A is fixed here and end D is having an hinge support. So whenever we are having a support other than the fixed support, we know that we have to make or the final end moment about this point where whether it is a hinge support or a roller support or a simple support, the final end moment will be equal to 0. So what we have to do here is we have to consider an additional moment so as to the final end moment about this point will be equal to 0. So we have to consider the modified fixed end moment, that is the fixed end moment from D to C we have got here. How much that is? Plus 37.5 kilonewton meters. So now if I want to modify, that is M dash F DC plus 37.5, what we need to do here is we have to apply equal and opposite moment so that the value or the final end moment will be equal to 0. Next we have to find out the modified fixed end moment for C to D. So from moment distribution method we know that whenever we are considering an additional moment, half of that moment has to be carried to the other end of the same member. So here we have got the fixed end moment from C to D is minus 37.5 plus half of the moment whatever we have considered here, that is minus 37.5, which will be equal to minus 56.25 kilonewton meters. So the next step will be to calculate stiffness, that is K, and rotation factor, which is represented by U. So for that I have taken a table here where I need to consider the joint and the member for that particular joint, and for that particular member we need to find out the stiffness K and the rotation factor. So if we observe in this beam here, we are having two joints, that is joint B and joint C. So considering the first joint, that is joint B, where B is connected to a member from B to A and from B to C. So B to A is one member. Similarly, B to C is the another member. Similarly, for span or for joint C, we are having a member C to B and C to D. So for this member, we have to consider the relative stiffness. So for that, we have to see the far end conditions. If I consider for member BA here, B is the near end here and A is the far end. So B is the near end here and A is the far end. Since the far end is fixed here, we know that for fixed end, the stiffness will be equal to I by L. So the moment of inertia I is given for the span BA here is I, which will be equal to I by the total span here is 4 meters, which will be equal to 0.25 I. Similarly, for span BC here, since B and C are the intermediate supports, if I consider the B here, if I take the B here, which is the near end, and C is the far end, and in structural analysis we know that even the intermediate support is considered as an fixed support. So for the, since the far end is fixed here, the moment of the stiffness will be equal to 2I by L, because the value of moment of inertia is given as 2I, that will be equal to 2I by the total span, that is 4 meters, which will be equal to 0.5 I. For member CB, the value here is same because C is the near end and B is the far end here. Since the far end is an intermediate support, we are taking that support also as an fixed support, which will be 2I by L, that is 2I by the total span is 4 meters, 0.5 I. So for span or member CD here, C is the near end and D is the far end. Since D is a hinge support, so for hinge support we are considering the stiffness as 3 by 4 into I by L. We have to note here is that only for the fixed end we are considering 100%, and for whether it is a hinge support or a simple support or a roller support, we are considering only the 75% of the value, which will be equal to 3 by 4 into I value here is 1.5 I divided by the total length is 3 meters, which will be equal to 0.375 I. So whenever we add the member BA and BC for the joint B, we are going to get the total stiffness about the joint. That will be 0.25 and 0.5, which will be equal to 0.75 I. Similarly, 0.5 I plus 0.375 I will be equal to 0.875 I. Now, if we need to find out the rotation factor, which is given by U is equal to minus half into K by sigma K, that is K by sigma K is nothing but the distribution factor. We can consider one more table here if you want to find out K by sigma K. Otherwise, we are directly applying the values here. So, for member BA, the value of rotation factor will be equal to minus 0.17. For BC, we are having a value of minus 0.33. So, whenever we take into consideration this one should be equal to 0.5 and the total value should be equal to 1. So, for member CB, it is minus 0.27. For member CD, it is minus 0.23. So, the next step will be to construct a Kanis table or a rotation contribution table. So, what we have to do here is, in the construction of Kanis table, we have to replace the intermediate supports with the help of the boxes, and we have to first write the fixed end moment, whatever we have got in the first step here. Say for example, we have got fixed end moment from point A to B, that is the value was minus 17.58. Similarly, fixed end moment from B to A, the value was 20 plus 29.29. From B to C, minus 106.67. From C to B, it was plus 106.67. From C to D, we have to write the modified fixed end moment, whatever we have got, that is minus 56.25, and D to C it is 0 since it is an hinge support. So, what we have to do here is, in the construction of Kanis table, first we have to take the summation of the fixed end moment about this joint here. So, plus 29.29 and minus 106.67 will be equal to minus 77.38. Similarly, here plus 106.67 minus 56.25 at joint C will be 50.42. So, here in this box here, we have to represent the rotation factor whatever we have got for member B to A in the table 2, the step 2, which was the rotation factor for member B to A was minus 0.17. Similarly, from B to C, the rotation factor was minus 0.33. From C to B, the rotation factor is, as we have calculated, is minus 0.27, and from C to D, we have got minus 0.23. So So now what we have to do here is we have to calculate the rotation contribution, and we have to remember that the rotation contribution is calculated only for the intermediate supports and not for the end supports. Say the rotation contribution about A to B, which will be represented as M dash AB, here M dash BA, because here from A to B, B to A, here rotation contribution from B to C, rotation contribution from C to B, here rotation contribution from C to D, and rotation contribution from D to C. Since we are calculating the rotation contributions only for the intermediate supports, the end supports rotation contribution will be equal to 0 here. Now if we want to calculate the rotation contribution, we know the formula, that is rotation contribution about any point, which will be equal to a rotation factor multiplied by summation of fixed end moments plus summation of far end rotation contributions. This is the formula which we have to use here, and we have to carry out the iteration process so that we can arrive at the rotation contributions at that particular intermediate supports. So if I consider this rotation contribution from M dash BA, that is from B to A, going for the first iteration, call it as cycle 1. So here M dash B to A will be equal to the formula here, the rotation factor. Rotation factor from B to A here is minus 0.17 into the summation of fixed end moment. That is this summation at fixed end moment, which we have got. That is minus 77.38, and the summation of far end rotation contribution for this point or joint support B, which is the far end here for B. The far end here is this one, M dash AB. Similarly, the far end for at B here, one more is M dash CB. So we have to take into consideration these two values are the new iteration values whenever we are calculating the iteration process. So for similarly here about point C will be M dash BC, and here M dash DC. So these values I have to take into consideration. So here M dash BA will be equal to the rotation factor we have got, it is minus 0.17 into the summation of fixed end moment plus summation of far end rotation contribution. Here the far end rotation contribution is how much? 0. And about this point we don't know, we need to calculate. So the first cycle value will be equal to 0, which fetches a value of 12.92 kilonewton meters. So this value will write here, that is 12.92. Similarly, M dash here, this one, BC will be the rotation factor. Here the rotation factor is minus 0.33 into the summation of fixed end moment, that is minus 77.38 plus 0, which will be equal to 25.77 kilonewton meters. This value we have to write here, 25.77. So next we have to calculate the rotation contribution here, M dash CB, which will be equal to the rotation factor here is minus 0.27 into the summation of fixed end moments, which is 50.42 plus the summation of far end rotation contribution. Here the far end rotation contribution we have got a new iteration value, which is 25.77 0.77 plus this value here, foreign rotation contribution, which is equal to 0. So the value will be minus 21.79 kilonewton meters. Similarly, M dash CD, the rotation factor here is minus 0.23 and the summation of fixed end moment 50.42 plus the new iteration value which we had got, that is 25.77 plus 0 will be equal to minus 16.3 kilonewton meters. So this value we have to write here, that is minus 21.79 and this value minus 16.3 kilonewton meters. So now we have to go on repeating the iteration process until and unless we get the same and equal values here. It may come for the second cycle or the third cycle, we don't know. So we have to go on continuing the process. So here if we go for the second cycle, if we consider the second cycle, everything remains same here except these new values or the new iteration values or the new values for the far end rotation contribution only changes. That is, if I go for M dash BA here, the value U remains same and the summation of fixed end moments remains the same. Now I have to consider the new value here, that is the far end rotation contribution, that is 0. First one is 0 and the second value here, if I take the new iteration value here, is for the far end rotation contribution, that is minus 21.79. So we are having a value of 16 plus 16.56 kilonewton meters. So this value we have to write here, 16.56. Similarly, everything remains same here, only the new value or the new iteration value will be added, which will be equal to 33.02 kilonewton meters. So this value we have to write here, it is 33.02. Same for here also. That is M dash CB will be equal to, the rotation factor value here is minus 0.27 summation of fixed end moment plus the far end rotation contribution here is 0 and the new iteration value or the new value for the far end rotation contribution here is 33.02, that is plus 33.02, which gives a value of minus 23.86 kilonewton meter. So this value we have to write here is minus 23.86. Similarly here for M dash CD, everything remains same. So the value will be equal to minus 17.86 kilonewton meters. So this value we have to write here, minus 17.86 kilonewton meters. Sorry, here I will not take into consideration the units, only the values I will consider here. So if we observe here, in the cycle 1 we have got 12.92 and in the second cycle we have got 6.56. So we have to carry the iteration process where we are getting the equal values here. So going for the third iteration process or for cycle 3, here everything remains same, only the new iteration value will be taken into consideration. So plus 0 minus 23.86, which will be equal to 16.91 kilonewton meter. So this value will take here 16.91. Similarly, plus 0 minus 23.86, which will be equal to plus 33.71 kilonewton meter. So this value 33.71. So here there is the far end rotation contribution here is 0, and the summation of fixed end moment here is 50.42. The rotation factor is minus 0.27, and the new iteration value here is plus 33.71, where we get a value of minus 24.04 kilonewton meter. So this value we will write here minus 24.04. So this will be plus 33.71, which will be equal to minus 18 kilonewton meters. So here we will write minus 18. So we will go for the next cycle. So here everything remains same, plus 0. Here the new iteration value, that is minus 24.04, which will be equal to 16.94 kilonewton meters. So we will consider here 16.94, 0 minus 24.04, which will be equal to 33.78 kilonewton meters. 33.78. So here repeating the same process, plus 0 minus, plus the new iteration value here is 33.78. The value will be minus 24.08. So here minus 24.08. So here plus 0 plus 33.78, which will be equal to minus 18.02 kilonewton meters. So minus 18.02. So now if we observe here, the values are almost similar. So probably if we take or carry out one more cycle, the values will be equal here. So here this value here, in the fifth cycle M dash BA, there is a far end rotation contribution here will be 0, plus the new iteration value here is minus 24.08, which will be equal to 16.94. So 16.94 is kilonewton meters. So here plus 0, here this one value, this is minus. So here also minus 24.08, which will be plus 33.78 kilonewton meters. So here 33.78. So here also if we follow the same procedure, plus the new iteration value here is 33.78, which will be equal to minus 24.08 kilonewton meters. So plus 0 plus 33.78, which will be equal to minus 18.02 kilonewton meters. So this value we will consider here, plus 24 minus 24.08 minus 18.02. So since now we have got the same values here, we can stop the iteration process here, because the further we go in the iteration process, the value remains same. So this value which we have got, the rotation contribution, see here, see these values whatever we have got here, the rotation contributions, this we have to consider while calculating the final end moments. So these values have to be considered while calculating the final end moments. So our last step, it is step 4. Our last step will be to find out the final end moments. To find out the final end moment. So to find out the final end moments, we know that if we need to find out the final end moments, we have the formula, that is fixed end moment about that particular point, whatever we have to find out the final end moment, plus 2 times the rotation contribution about the near end, plus 1 time the rotation contribution about the far end. So the rotation, so the fixed end moment about point A to B we know, which is minus 17.58 plus 2 times the rotation contribution about the near end is 0, that is m dash AB, plus 1 times the rotation contribution about the far end, we have got the value here, that is 16.94. So the value will be equal to minus 0.64 kilonewton meter. So similarly, following the process to find out the final end moments, I will just write the value here. The final end moment from B to A will be equal to 63.17 kilonewton meter. The final end moment from point B to C will be minus 63.17 kilonewton meters. Similarly, final end moment from point C to B will be equal to 92.29 kilonewton meter. From C to D will be minus 92.29 kilonewton meters. Whenever we are calculating the final end moment about point C to D, the fixed end moment have to be considered, that is the modified fixed end moment has to be considered here while taking the values. And the fixed moment from D to C, we know it is 0 since it is an hinge support. So just representing the values here, that is at AB, it is anti-clockwise negative, that is minus 0.64 kilonewton meters, and from B to A it is positive 63.17 kilonewton meter. C to B, which will be having an equal and opposite moment here, we have to cross check here about the joint. If you are having the equal and opposite moment, then the calculation is correct. So from C to B, Here the value is 92.29 kilonewton meter. From C to D it is minus 92.29, and about point D to C it is, the value is 0. So next, if you want to calculate the bending moment and support reactions also, by using these values we can calculate the support reactions and the maximum bending moment also. So similarly, we shall see some other numericals related to the Kanis method in the coming classes. Thank you.